The last topic in chapter 10 is based on the Bernoulli equation. Now, Daniel Bernoulli was a member of a family of Swiss mathematicians. He lived to be 82 years old. He was born in 1700, so he had a very long-lived life, and he did marvelous things. He used Isaac Newton's ideas and the law of conservation of energy to come up with an equation which is used in aeronautics, in other words, airplanes. And the idea is when air flows over a surface, there can be a difference in the pressure. In the case of an airplane, when the air flows over the top of the wing, it's designed so it travels faster. And as it travels faster, the pressure goes down. Under the wing, what happens is the air travels slower and there's a higher pressure, so the pressure on the bottom is greater than the pressure on the top of the wing, and it causes lift. In other words, the airplane can lift off the ground. And so this is the Bernoulli equation. It's based on the law of conservation of energy, but in your textbook, it looks like this, and I hope you can read it right here. There's the pressure. This is a problem involving a house. You have over the house, the air is flowing at 30 meters per second over the roof. So there's a decrease in pressure there. Under the roof, there's no air flowing. And also, anytime I do this problem, I always think of Hurricane Andrew. Because when Hurricane Andrew occurred, you could see where my roof had lifted off a bit and settled back down. Now that was 1992, August 24th, 1992. Well, here's what the equation says. The pressure on the bottom is greater than the pressure on the top, so that's going to create a lift on the roof. It's equal to 1/2 the density of the air, in this case, because it's air, the velocity over the roof, which is 30 meters per second, minus the velocity under the roof, which is 0, because under the house, no air flowing through the house, plus the density of the air times gravitational acceleration times the thickness of the roof. Now the thickness of the roof is usually very, very small, but since I have it in there, I decided to put in a number because students always want to know what the number would be. So it says use this equation to determine the difference in pressure between above the roof and below the roof. So in this particular case, we read the problem, and I'm going to read the problem now. This is problem 27 in the textbook. Okay? So let me get the problem out and read it very, very carefully. A wind of 30 meters per second, which is about 67 miles per hour, passed over the roof of a house that has a surface area of 200 square meters. The wing is, well, it should say the roof is 0.5 meters thick, and the density of the air is 1.29 kilograms per cubic meter. Now that would be the density of dry air. Determine the lift on the roof, and then I have the answer there. Okay? So now using the equation, I go down here, there's the difference in the two pressures. 1/2 the density of dry air, 1.29 kilograms per cubic meter. The speed of the air over the roof, 30 meters per second. The speed of the air under the roof is 0. And then the thickness of the roof was 0.5 meters. And so this is the actual density times gravity times the thickness of the roof. When you work this part out, this comes out to about 580 newtons per meter squared. This part right here is very small, about 6.3 newtons per meter squared. So the total difference in the pressures between the top and the bottom is about 586 newtons per meter squared. Now the question was not really to ask for the pressure difference, though you need that. The question was to figure out the lift, the force on the roof. So now what we do is we take the pressure times the area. Remember, the pressure is force divided by area. So in this case, we're going to have the pressure times the area that will give you the force, the lift. We know the difference in pressure is 586 newtons per meter squared. We know the area of the roof is 200 square meters. And when you multiply it out, I got a value of about 117,000 newtons. Now my calculation in the textbook was 116,000 newtons, but I think that's close enough for our purposes. Now in this Bernoulli equation, you could use it all sorts of things. Chimneys. What happens there travels over the chimney, creating a low pressure, and what happens is smoke will go up the chimney and out into the open air. So that would be an example of that. Also, blood in your arteries, for example. If the arteries begin to get clogged, what will happen is there'll be a reduced, the velocity will go up, there's a reduced pressure, and the artery can get closed up. Now, if you read the applications at the end of chapter 10, I think I talk about the one where it's called vascular flutter. And a cardiologist can actually listen to your heart and notice that the arteries are opening up, closing, so vascular flutter, and then it can realize that the arteries may be getting clogged. All right. Now, the interesting thing again about Bernoulli was he lived to be 82, good health, which was rather unusual for life that long at that time. But since I'm almost 80 years old, I hope to beat Daniel Bernoulli by a number of years. All right, and so that's the end of this lecture, end of chapter 10.